Okay, let's start. Okay, I'll start speaking. So we have to do the close string. And then everything else I promise I will say. So let's see where we get. Because the idea is to start with the superstring tomorrow. So, okay, how do we construct the states? So we said it. So alpha minus n1, mu1, a bunch of alphas, nu I, and a bunch of alpha tildes. So now we have the alphas and the alpha tildes. 1 nu 1, alpha tilde nu k minus mk. On this, and they have polarization tensors, mu I, mu1, mu k, that have certain symmetries and certain properties for these to be physical states. And the physical state conditions are just two copies of the ones for the open string. So L phi equals 0 for all m greater than 0, and L tilde m phi equals 0, L tilde 0 phi equals to a phi, L 0 phi equals to a phi. And this A appears in the same way as in the open string from this commutator, so A is the same. And A is the same for the left and on the right, because it's the same type of commutators that you do. And so we anticipated that A was equal to 1, so A is equal to 1. And again, we'll see that there was this issue of the eta mu mu, so there was this issue here that is half erased of this t minus 2. So we'll see that. So this condition, the L0 condition, usually one adds and subtracts them. So there is, and yeah, there's something. So again, L0. Where should I write it? Let me write it here. So L0 is. And now I should get the factors right. So I think here is p squared over 2. Yeah, for some reason this coefficient is, and I forgot to check where was the factor of 1/4. But here it should be p squared over 2 plus this operator n equals 1 to infinity, alpha minus n, alpha n, that we call n. And then and then without the a, the minus a there. So and L0 tilde is the same, but with the alpha tildes, but the P is the same. So P is the center of mass momentum, and so there is no P and P tilde, P is the same. And so P squared on the state is going to give me K squared on the state, and then the mass shell condition, so this condition says that also, so it tells you what the mass is, because K squared is minus M squared. So it's useful to sum these two. So this is, so it's 2a. So the condition is this, and this is 2 phi. And this condition is going to, so doing the same as before, so p squared is k squared is minus m squared. So this will say that m squared is 2 over alpha prime n plus n tilde minus 2, where n is the eigenvalue of the operator n tilde is the eigenvalue of the operator n tilde. So n will come here, all the n's that we have will be the sum of n1, n2 up to ni, and n tilde will be the sum of m1, m2 up to mk. And up to here, n and n tilde could be anything, and they are not related to each other. I can put alphas and alpha tildes as I want, but if you subtract this condition, L0 minus L0 tilde on phi, this has to be 0, right? Because the a's cancel. And when you do this, the p square cancels. So this condition says that actually n is equal to n tilde. And so the total number of oscillations is equal to n tilde. So I could have something that has alpha minus 1, and alpha tilde minus 2. That's allowed by this condition. This condition is called level matching condition. So the level on the left and on the right have to be the same. And it's the only condition that mixes left and right. The other, so left lives its life, right lives its life. But this level matching condition tells you that not completely. So you need to have these levels to be the same. Okay, so we start at, so the lowest state has n equals n tilde equals 0. So this is the 0 of the closed string. And it's defined such that it's annihilated by all the annihilation operators. So this state is, these conditions are automatically satisfied. And this condition, so n equals n tilde, and this condition tells me that that state has mass squared equals minus 4 over alpha prime. So we also have a closed string tachyon. So, okay, bad state, but we know that the bosonic string is not a good theory. So that will be all right in the superstring. The next level is n equals n tilde equals 1. And this is, so phi equals e mu nu alpha mu minus 1 alpha tilde nu minus 1 on 0. I can also think of this e mu nu as so e mu tensor e tilde nu. So it has two indices, and since these are different, they commute, and an alpha is different from an alpha tilde. This polarization tensor has no particular symmetry. So now let's see the physical state conditions. Well, first, so the L0 plus L0 tilde on phi equals to phi gives me this mass condition, and I have that this state is massless. So spin 2, massless particle, that's nice. And then from the LM condition, the only one that is going to be non-trivial is L1, right? It's the same as, so it's like a tensor product of the massless state for the open string on the left and the massless state for the open string on the right. So the condition I will get, so from L1 phi equals 0, so L1 will act on this mu index, so, and it will bring me back a k mu. So this will tell me that E mu nu k mu is equal to 0. So you can forget about the right, and this is like the vector. The condition tells you that E mu k mu is equal to 0. And the L tilde 1 phi equals 0 is going to tell me what? Yeah, exactly. So E mu nu k nu is equal to 0. So either index contracted with a k has to be 0. Okay, I don't think we'll need this. And so this says that each one of these indices has d minus 1 polarizations, but there are null states, right? How do I construct null states? So E mu nu how do I construct null states? Right, so I either put the mu index to be, so let me call it A mu k nu plus k mu b nu, but as long as, so A mu k mu has to be 0 and B nu k nu has to be 0. So these states are physical. You contract with k either here or here, and it gives you 0 because k squared is equal to 0. So it's m squared equals 0, which means k squared is equal to 0. And each of these indices along k, as long as the other is also orthogonal to k, then these are null states. So then E mu nu has d minus 2 times d minus 2 components, right? Each index can run, I can do the I can do the Lycon gauge. It is in, I mean, it's the tensor product of the massless open string with a massless open string. But now, so this is not any reducible representation of so D, the little group, so orthogonal to the Lycon gauge, or sorry, not the Lycon gauge, orthogonal to this Lycon, we have the 8 directions that I call I, so there is some SO8 inside SO1,9. So we're looking at here at SO8 inside SO1,9. Yeah, sorry. Thank you. Good. Or let's say SO D minus 2 inside SO 1, comma D minus 1. Yeah. Thank you. Yes. Yeah, sorry. Too used to the superstring. And SO8 is so nice that I really want to do SO8 instead of SO24. Okay, so the irreducible components are what? I mean, this can be symmetric, symmetric traceless, anti-symmetric, or you can take the trace. So those are the irreducible components. So if you're used to Young tableaus, it's this, and the trace. So this is the symmetric. This is the so symmetric traceless. So mu nu symmetric, and then mu nu eta mu nu is equal to 0. The anti-symmetric mu nu. So you understand, I put I put in the symmetric, so in this symmetric, this could correspond to mu nu times alpha mu minus 1 alpha tilde nu minus 1 plus alpha tilde mu minus 1 alpha nu minus 1, right? This is what one is doing. And then this mu nu satisfies this condition. In this one here, you do the same thing with a minus sign. And then this is a trace. So here I have d minus 2 times d minus 1 over 2. So 24 times, okay, let's put it in terms of d. Sorry, d minus 2 times d minus 1. Here I have d minus 2 times d minus 3 over 2. And sorry, I forgot the minus 1 because this is symmetric traces, and this is a 1. And if we look at these null states, I mean, so this is a quanta of some gauge field. This gauge field is symmetric and has 2 indices. This gauge field is antisymmetric with 2 indices. And this is some scalar field. I mean, let's see what are these gauge redundancies. So if I want the symmetric part, so for the symmetric piece, then what I have to do is to take B mu equals to A mu. I take B mu equals to A mu. And let me call this xi mu, just to see if you recognize this. So I have, so xi mu, let me put this first, k mu xi nu plus k nu psi mu. So if I go to the field, this is like a derivative d mu psi nu plus d nu psi mu, because this k mu corresponded to some derivative. And do you recognize this kind of gauge transformation? Yeah, you're all nodding. What's yeah, so these are killing vectors, or I mean, so we are doing everything linear, but if we put it like this, now let's go to the field. So these are diffeomorphisms. So again, here we have partial derivatives because we are in flat space. But if you write it like that, so this gauge, so these null states for the symmetric tensor corresponds to the gauge redundancy of diffeomorphisms. So these are the gauge redundancy of space-time diffeomorphisms, right? So this is very different from the worksheet. So we have a massless spin-to particle, which is some sort of gauge field, and it's gauge transformations. We're not used to call it a gauge field, but sort of gauge transformations are diffeomorphisms. So the field corresponding to this quanta looks like the metric. And we'll see more that it makes sense to recognize this as a metric. So the gravitons, so this is the graviton. So we recover the graviton as an excitation, a closed string that has a left moving mode with the lowest frequency and a right moving mode with the lowest frequency, and they are such that their excitations are symmetric so this polarization is symmetric in mu and nu. Now, if we look at the anti-symmetric piece, I want to take B mu, mu equals minus A mu, and let me call it, so the B mu is better to put it first. So, okay, so let me call this lambda mu. Instead of psi mu, I call it lambda mu, just because we're more familiar with this. So this says that E mu nu is like E mu nu plus, so the part, so K mu lambda nu minus K mu lambda nu. So if we go to the field, so this is a field that, unless you saw string theory, you haven't seen before. The field is called the B field. Can you see here? Or it's too small, yeah. So the field is called B field. And it has this gauge transformation. So it has two indices. So the gauge parameter has one index. So it has, so this is a two form. If you saw the language of forms, this is a two form. So the two form is an antisymmetric two tensor. And its gauge transformation is a one form. So this is called B field. And why didn't you see it in, so in 4 dimensions, so we will see that this field satisfies should I go ahead and, okay, maybe let's say it later. But in 4 dimensions, this is equivalent to an axion, because you can, there's a field strength that is going to be a 3 form that you can dualize in 4 dimensions to a 1 form as the derivative of the axion. But in 26 dimensions, that's not true. You can dualize this to what, 3, 26 minus 3 minus 2, 26 minus 2, no, 26 minus 3 field, so it's not much better. Okay, and I'm going to say more about this field, which appears, I mean, this metric will also appear in the superstring, this quanta, this will also appear in the superstring. And the last one is, so if I write the fields here, yeah, maybe I should. So this is the graviton. This is the B field. I don't know, B field photon. This doesn't have a name. The we talk about B field, but the quantum of it, there is no name for the. And the trace, we call it phi. So B field, so graviton G mu nu, B field B mu nu, and put phi here, and this is called the dilaton. I will play a very important role. And then you can keep going and requiring the physical state conditions. It's more painful because, well, the next level will be n equals n tilde equals 2. And then you can play with alpha minus 1, or alpha minus 2. So you have many states and it becomes more painful, but you can do it. And you also have, so in the closed string, you also have a tower of states. This is m squared equals 0. They are more separated. So this is m squared equals minus 4 over alpha prime. The next one has 4 over alpha prime, right? The next one will be 8 over alpha prime. etc. So you have a tower of states. And again, if you want to do low energy theory, low energy effective theory, you restrict to this massless sector. Okay, so the massless spectrum of the closed bosonic string is given by this, and the open bosonic string, and in this, so open bosonic string, we have this vector field in the adjoint of some gauge group that we saw. UN is the simplest to get. Okay, questions about this? Yes. You can, I mean, you can do, so you mean that LM phi is equal to 0 automatically for all m greater than 2. Yeah, so you can do it with this commutator, Lm alpha mu n, which was minus n, alpha mu m plus n. So this raises this raises whatever alpha by m's. So if you do L2, then you commute and you will end up, once the L2 acts on here, it annihilates, and then when commuting, you're going to end up with an alpha 1, and that annihilates. Yeah, I don't know if for formal, I mean, more than this, or I guess you can do it iteratively. No, because ln is lm plus n. Yeah, I don't know. Well, but with that, yeah, it's easy to show that all the others are satisfied automatically. Yes. Mm-hmm. Mm-hmm. So you have to require both conditions. If you take one condition separately, it gives you the mass. So this will give you the mass in terms of n tilde. This will give you the mass in terms of n. And then you can do the difference of them, and that will give you that n is equal to n tilde. Then if you want to understand it physically, what it means is that the string should be invariant under translations. Because, so L0 are the mode, is the zero mode of the energy momentum tensor. Yeah, how you can see that. It's the zero mode of the, left moving energy momentum tensor, or is it's like the Hamiltonian on the left, this is like the Hamiltonian on the right. So this difference is associated to translations. There's a simple way you can see that. Well, there's a simple way that you can see that, but now I'm... but yeah, that's the physical... That's that's how you understand this. But you have to impose, so the physical state conditions are these. So I can impose them separately, or I can do sums and differences. It's the same, right? So if you do it like that, one will tell you that m squared is 1 over alpha prime and minus 1. The other will tell you that m squared is 1 over alpha prime and tilde minus 1. 2 over alpha prime, right? Because this was p squared, yeah. And then since m squared is the same, these things have to be the same, so n equals n tilde, and I can write this as 1/2 of n and m tilde. Well, I hope yeah, there should be a 4, right? There should be a 4, yeah, 4. So then, right, because this is p squared, well, again, this factor of 4, p squared over 4. Okay, now is this correct? Yeah, this is correct. So yeah, you can do some differences. Yeah. The two masses, so m squared is equal to minus k squared, and k is the same, yes. I mean, probably this, oh, no, never mind. I was going to say something. Okay, yes. Yeah, we don't know, and yeah, the fact that we haven't found it yet means probably that there is no such thing, and this is just an inconsistent theory. But yeah, in principle, a vacuum could mean that you just go somewhere else in the theory, and yeah, where it disappears or condensates. But yeah, here for the bosonic theory, we don't know where that somewhere else is. So. Okay. So now there are many things I want to say today if we want to start with the superstring tomorrow, but let's see. I mean, these are important things. So one is this, there's a quick way to find the spectrum. So at the end of the day, we get representations of SOD minus 2 for massless states. And actually, if you do massive states, then you will get representations of SOD minus 1. But it's always arranged in representations of SOD minus 2 somehow. Yeah, maybe that's a little bit confusing, but so, I mean, there is if you want to count real physical states, so taking out the gauge redundancy and taking out the non-physical states, there's an easy and dirty way to do it. To count the number of physical states. So again, why do we have these null states? We have these null states because we have this conformal invariance, which is a redundancy. So there is an easy way to gauge fix this conformal invariance, which is to use Lycon gauge. To fix the residual conformal invariance. And once you have done that, then there are no more null states. So for this, you define Lycon, so space-time, Lycon coordinates. So we are in flat space, so let me take x0 and x1. So, and I define x plus minus to be 1 over square root of 2, x0 plus minus x1. So these are Lycon coordinates. And then the rest, I call them xi. So I goes from 2 to d minus 1. And now let me think of the field, the worksheet field, which is the embedding coordinate. So x plus, that depends on tau and sigma, that has excitations along the plus direction. And this decomposes into an x plus left that depends on sigma plus. And let me call this sigma left. So sigma left is what we call sigma plus, so tau plus sigma. And x plus right, that depends on sigma minus, or sigma minus, which I call sigma right. Not to confuse these pluses and minuses. So this plus and minus I use for Lycon coordinates in space-time, and not to confuse with the Lycon coordinates on the worksheet. So the Lycon coordinates on the worksheet, I'm going to call them sigma left and sigma right. And I'm going to use, so their conformal symmetry doesn't mix sigma left with sigma right. So the conformal symmetry was defining sigma left tilde, which was some f left of sigma left. Sorry, I'm left. And sigma tilde right, which was some f right of sigma right. And I'm going to do some horrible thing such that at the end of the day, so this x plus, so this function has so the center of mass momentum, the center of mass position, and the oscillators along alpha plus. And what I'm going to do is do some horrible conformal transformation such that x plus, that depends on sigma, so x plus, sorry, left, that depends on sigma left, or sigma tilde left, I mean sigma or sigma tilde left. Let me write, so in terms of sigma tilde left, I'm going to do this transformation such that this is just sigma tilde left. I'm allowed to do that. It's some horrible transformation, but I get rid, with that I get rid of all the oscillators. And x plus right, that depends on sigma tilde right. I want it to be sigma tilde right over 2. So this means that x plus depends on sigma tilde, which is again x plus left plus x plus right, is sigma tilde left plus sigma tilde right. Sigma left is, well, sigma tilde left is tau tilde plus sigma tilde. Sigma right is tau minus sigma. So if I add this, what I get is just tau tilde. So this is tau tilde. So this means that what I'm with this parametrization, then what I have is that p tilde is equal to 1. P tilde plus, sorry, p, not p tilde. P plus is equal to 1. And p minus is something. If I want to compute the norm of p, I have to do p plus and p minus. So p minus, I haven't talked about p minus. and there are no oscillators in the plus direction. I mean, this is a bit awful just to say something, but I wanted to believe it. I wanted you to believe it. If this is too complicated, just take the take-home lesson. So I have done this, and now I can require the constraints that T, plus plus, or let me say, so T alpha beta equals 0, which this is, so it's X. So it's X dot square plus X prime square equals 0, and X dot, contracted with X prime equals 0. So I can write this in this way. And if you do this, I can get X minus as a function of the xi. I mean, I'm writing the solution. So what you get is that alpha minus n is 1/2. This is not very important, but alpha I n minus m, alpha I m minus a delta n 0. Something. The important thing is that you can use the conformal symmetry, so these conformal transformations, and this constraint to get rid of the oscillators alpha plus and to write the oscillators alpha minus in terms of the alpha I. So when you have to count the number of physical states, you can either start with alpha mu and require the physical state conditions, or just whenever you have an alpha mu, put an alpha I. So the take-home message is that the dirty way okay, or let's say the easy way. So the easy way to count number of physical and non-redundant, so the states in the Hilbert space, no redundant states, is that whenever you have an alpha mu minus n, you count as if this was alpha I minus n. So this counts as d minus 2 degrees of freedom. And this you can do for the massless. I mean, for the massless, we work this out. But also for the massive states, it works. But at the end of the day, the massive states should combine in such a way that you get representations of SOD minus 1, not SOD minus 2. But that's by combining, so for example, if you combine this alpha minus 2 with the alpha minus 1, alpha minus 1. So if you count the number of states, here you have d minus 2, and here you have d minus 2. So this is symmetric, d minus 1 over 2. And again, these are representations of SOD minus 2, but you can combine these two. That's actually an exercise. Out of the sum combination of these, that gives you representations of SOD minus 1, which is a little group of massive particles. But okay, so all this to say, you want to count the number of states, just do this. Quick and dirty. Count the number of physical, non-redundant states. If you just want that, don't go through the pain of requiring the physical state conditions, just do this. and it works. Okay, and one last thing, and then we take a break, and then the second half will be a lot of things condensed in 45 minutes. So now this I said, so when you want to compute A, so A was minus 1/2 of the sum from n equals 1 to infinity of n, and this was an eta mu that we got from this. So this thing here is a commutator of alpha mu n alpha nu minus n, and then eta, sorry, this is eta mu mu, eta mu nu, right? When you do L0, then you get by commuting the alphas n and the alpha minus n, this is what you get. So I said this is equal to minus 112. And now if I want to count physical degrees of freedom, instead this I have to put alpha I n, alpha j minus n, and a delta of ij. So this is a delta of ij. So this gives a d minus 2 over 24. So this is A. And now I said anticipate A equals 1. And that gives d equals 26. But okay, this is a bit circular. How does d equal 26 arise? Well, if you do quantization with gauss, the gauss have central charge minus 26, and so that means that, and the central charge of this system is equals d, so that means d equals 26. And there's also a third way of seeing another way. A third, this is not really a way. Then, A equals 1 gives nice result, gives massless states, but it doesn't tell you that that D has to be 26, that A has to be equal to 1. But there is another way of getting D equals 26, which is from demanding conformal invariance at one loop. And this is what I'll try to do after the break, but very, very, very sketchy it will be. Questions about this? This was fast and a bit sketchy, but you can. This is the take-home message. Yes. It's just that you have to do it properly, actually, or when you do LM and you sum over, when you expand in modes, you should only expand in the actual physical modes, which are these D minus 2. Again, this is a bit quick and dirty, but yeah, good question. I don't remember. I saw all covariant quantization a long time ago. Yeah, good question. I'll take a look and I'll tell you. I'll tell you later. Yeah, but you should be able to see it also doing covariant things. Yeah, I'll tell you. Yeah. Okay, so we resume at 5. Take a 5-minute break. A 40-minute condensate of a 2-hour class that is already a condensate of a longer class. So let's see. Let's see. Yeah, sure. And that I erase. Yeah, so yeah. No, 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 no. No, and then you can do, yeah, you can do this exercise 3 point something. Well, I can tell you like it's 3.5. Is precisely go at level n equals to 2 and count. I mean, this is what I wrote, the alpha minus 2 and the alpha minus, and then see for any d, this you can recombine them in such a way as to get representations of SOD minus 1. This works for any massive state. Yeah. Yeah. I mean, no, in principle, no. Now there's now more a bit of more math on these higher spins and some way of accommodating them in something, but it's not. It's really not straightforward. Yeah, you have to work it out. So yeah, I don't have a, yeah, the quick answer is no. And somebody else can give you a longer answer like yes, but then it will take a 1 hour seminar of what can you do a little bit more, but yeah. Okay, so one thing is scattering amplitudes. And of course, we're not going to compute any scattering amplitudes, nor I'm going to mention all the ingredients that go into the scattering amplitudes, but there's only one thing that I want to say. So, I mean, you can, I don't know, you have 3 closed strings, scattering and going into 2 closed strings. And this process can, so this calculation of 3 incoming strings, which can be, I don't know, 3 tachyons going into, well, 2 tachyons, well, let's say 2 tachyons and a massless states going in. So there should be conservation. So you get conservation of energy and all the nice things that you get in point particles. But what I wanted to say, and let me do something simpler. Let me do 2 going to 2. This process, you can, so what can happen? These 2 can combine into a single string, closed string, and then the single string decomposes into 2. Or these 2 can combine in one string. This string now decomposes into 2. And I'm very bad at drawing. I should have started from the open string where the drawings are simpler. So here now this string, intermediate string, is decomposing into 2 and then combining again into 1. And etc. So this one, when this decomposes into 2, the one here can again decompose into 2 and then combine. And this is nothing but the loop expansion. So this is a 3-level. This is a 3-level term. This could be the 1 loop term, right? Because there is this intermediate process where there's one string that, so in point particles is this, right? One string that becomes, one point particle that becomes 2, and then, and these 2, so this could be something like this, and the same here. These 2, as long as there's conservation of everything that is conserved. So these two, these two here don't need to be, let's say if we put, so this is the same as if I put the thing here. These two don't have to be the same as this one, but with less energy. Well, in general, it won't be the same as this one. So you do, so in these scattering amplitudes, you do a Feynman diagram, so you sum over loops. It's just that each of these is finite, so things are much nicer. And also things are much nicer because, let me do, so if you do a closed string, an open string, and I want to do two open strings joining, so the scattering, the two scattering, so you have the same, the two combine into one and then they split, or I have this thing, and here there is a hole from, or I can put the hole in the middle. It's the same. Where you put the hole is exactly the same. So again, 3 level, 1 loop. And if you take this, so something that is not very hard to show, but I'm not going to do it. If you take these strings to, so t going to minus infinity or tau, well, yeah, t going to minus infinity. So the process, really the S matrix of 2 at minus infinity becoming 2 at plus infinity. There is a conformal transformation that takes this to a disk, and where each one of these is like a point. So this is a puncture disk. And this part we could do, but it would take, I don't know, 20 minutes. And so let's not do it. This is the same, but with it's a disk, but with a hole. So it's an annulus. Then the two loop thing will be something with two holes. Sorry? Yeah, exactly. These are vertex operator insertions that I didn't talk about. Yeah, so, yeah.
How are the strings interrupting? Is there some interruption?
Yeah, so yeah, this is the next thing I'm going to say, but yeah, but in this maybe this is going to be too short. But for each state of the string, there is a corresponding operator, vertex operator so there's a correspondence between states and operators, and yeah, and this is equal to this with these 4 vertex operators here. So I'm not sure that helps too much. But let me say, so there's one thing that I will say, and maybe that helps. So to say it, for example, a state in alpha mu minus 1 and alpha nu minus 1 can combine in some alpha mu minus 1, alpha nu minus 1 state, or alpha mu minus, or basically that's, so this will combine into some massive states. So you have these massless states, but with a given momentum, and this combines into this massive state, and then this can split again. And at the end of the day, things should be conserved. And this is, if you compute the scattering amplitude, you will get deltas. So you will get a delta of P1 plus P2 plus P3, or K1 plus K2 plus P3 plus P4, and then the polarization tensor should be such that also they combine in the right way. I mean, one has to do this calculation, which is not easy. I mean, I could write the 3-level scattering amplitudes for 4 tachyons, which is it's a famous scattering amplitude. But okay, one could talk about this for 2 classes. Let me. What I wanted to say is, so this and a little bit more. So the equivalent, the analog of the loop expansion and Feynman diagrams are these diagrams here. And here there's this diagram, by a conformal transformation, you can turn into a sphere with also 4 punctures. So that's a disk, and this is a sphere. This is a torus. And again, you have these 4 punctures that correspond to... Yeah. Good. I will, yeah. Good. Etc. So, and you get more handles. So if you do the 2 loop, it's something like this. You can do a conformal transformation and map it into this, and you always have these 4 punctures somewhere. Good. So what is expansion parameter? So if you do if you do loops, in general, in quantum field theory, expansion parameter is the coupling, right? The coupling constant. You do this perturbation theory in the coupling constant. So here is the same. But what coupling constant? I haven't talked about the coupling constant. So to see what's the coupling constant, we need something I'll say now, and then we'll need something that I'll say later. So the expansion parameter is also the coupling constant. But what is the coupling constant? So one very nice thing about this, so these are all Riemann, so these are all 2-dimensional surfaces, which are called Riemann surfaces, which is just, so these are locally like, so these are compact. First, they are all compact. Once you take these things to go to -infinity and +infinity, then this gets compact. And they locally look like C, like the complex plane. So one can write this in complex coordinates. But globally, they are very different. And this global thing, they're characterized by a single number, which is the Euler characteristic. Chi, which is the Euler characteristic, which is some topological number, which is 1/4 pi. Yeah, 1/4 pi. 1/4 pi integral. So if we write it in complex coordinates, the Ricci tensor of this surface that depends on some, so it's a Ricci tensor of a given metric that is, I can call it H, and it's the H. square root of, well, h or minus h, so here I'm taking Euclidean signature, so it's square root of h. So you can define different metrics for these surfaces, but they should be such that if you integrate this, so that's a topological number, and this is equal to 2 minus 2 times what's called the genus minus the number of boundaries. So this is the genus, which is the number of handles, and this is the number of boundaries. So the number of boundaries and the number of handles completely characterizes the surface, these Riemann surfaces. So that's all I need. And any metric that you can choose will be such that this number should be the same. Once you integrate this Ricci scalar over the surface, you get the same number. So this is genus 0, it has no handles, and it has no boundaries. So this is the sphere. So this one here is chi equals to 2. The sphere has this Euler characteristic equal to 2. And the fact that this is non-zero means that locally I can define a flat metric for the sphere, but globally you cannot. The sphere has curvature, and you cannot define globally. You cannot define a flat metric for the sphere. While for the torus has no boundaries, but it has one handle. So this is chi equals 0, which means if I want to make my life complicated and define some curve metric for some non-flat metrics for the torus, it should be such that after integrating its Ricci scalar, it should give me 0. So just define the flat metric. So you can define the flat metric everywhere on the torus. No, so this is independent of the punctures. The punctures, they don't change. I mean, think of the punctures as some, I don't know, as some little point there, but doesn't. So I'm talking about the topology itself. So yeah, the topology of the thing. Don't count the punctures don't change this genus. So that's not the way. Don't change this Euler characteristic. So if I have 8 punctures, it's the same. This will have a chi equals to 2. This will have chi equals 0. Yeah, yes. So this is I'm seeing this as a single worksheet. So this is this is the worksheet of one string with a worksheet of one string, combining and open it in 2 sort of worksheets. But now I want to see this as a single worksheet. And how does this worksheet? So I can take a parameter where I can I don't know. I can describe this with it's not very easy to see, but I can take. One could do it for the cylinder, and that's simpler to see than this thing. But now you can see the whole thing as a single worksheet. And so this I want to take all the way to tau going to minus infinity, or I want to take the parameter tau that goes from minus infinity, of this worksheet that goes from minus infinity to infinity. And then a parameter sigma that goes either from 0 to pi, if that's usually the thing. And then I can do a conformal transformation. I can do a conformal transformation that takes this, that takes this to the plane with a point at infinity, and that you can do a conformal transformation that takes it to the sphere. So it's how you parameterize the worksheet. And if this goes to, so this is non-compact if you take it like that. But if you take the things going to minus infinity and these things going to plus infinity, it's like the plane plus the infinity point that you can, it's a compact space, the whole plane plus infinity, and it's a conformally, so there is this holospherical, how is it called? The stereographic, right? Yeah, the stereographic projection that's equivalent to the sphere. So yeah, it's not hard to see. It's not easy to see that that this is equivalent. But it's not so hard to see with a cylinder. I mean, if it's one string going to one string, that's then is maybe it would be shorter if I do it. But yeah, let me not do it. But yeah, it's yeah, good. It's worksheet, yeah, yeah. So, yeah, yeah. So I'm going to say a little bit about that. Yeah, but these points are like, yeah, incoming. So you have two incoming states, which are a given. So a given state of the closed string. So this insertion will be different for depending on what kind of closed string it is. So it can be the closed string given by the alpha minus 1 and alpha tilde minus 1. And then so that will give a vertex operator here that is different if this was another closed string. Yeah, and that well, eventually this half explanation will probably take longer than the whole thing. But, okay. Infinite distance. I mean, right. So I mean, you can do a conformal transformation that takes the cylinder to the plane, but if you don't take the points at infinity, the plane is non-compact. What makes it compact is that you're taking this the infinite dimensional cylinder, then is the plane plus infinity, and that you can do a conformal transformation that makes it into a sphere. But yeah, it's the fact that you are taking, you're really computing S matrix. So 2 points, two strings at minus infinity that got into two strings. Okay, the two loops, so you add a handle, so every time you add a handle, the genus increases by 1, and the this Euler characteristic or Euler number decreases by 2. So this is chi equals to minus 2, and you keep decreasing the chi. So no, these have no boundary. So sorry, what do you? This you mean this boundary here? Yeah. So in the closed strings, this worksheet has no boundary. It's in the open strings that has boundary. So this has no handles, but it has one boundary. So this has chi equals to 1. And this is not a handle. By a handle, I mean this. So this is a handle. Not this is so this has two boundaries. So this is chi equals 0. This has 3 boundaries, so it's chi equals minus 1. And so so every time you add a loop, you get chi increases by -1 in the open string, while here every time you add a loop, so delta chi in going from loop n to loop n plus 1, this is -2. Yeah, very good. You can. So yeah, two open strings can join and give a closed string. So how do you see it as worse? It is not very, so it's like this joining and, I mean, I don't know, combining. Yeah, but in terms of this thing, what conformal transformation do you do? Yeah, good question. Right. So yeah. So you have to, yeah, you have to put two in the outside and one on the inside. But yeah, but still, yeah. Okay. Good question. I'm keeping. I should keep a list of questions that I'll. Yeah, but this can happen. Okay. Yeah. Let me keep going. Yeah, this is a weird. I mean, yeah, maybe it's easier to think of this. Yeah, so this is what he was saying. I mean, maybe that's, yeah, I guess that's probably right. And then, but from the point of view, so this would have chi equals 1. I mean, yeah, it's probably this. Yeah, because this, well, these punctures, I put it here, but that's, I mean, this doesn't have boundaries, so these punctures are sort of inside. While the punctures of in the open string, the punctures are always at the boundary. So yeah, I guess you're both right, and this is the equivalent of this diagram. Yeah, I don't see anything else that can be, but it's a bit weird. But okay, so I will change topics, but we'll come back to this because I haven't told you what the coupling constant is, but this will tell us what the coupling constant is. So keep these two things. So this is for the closed string. And for the open string is this delta chi in going from loop n to loop n plus 1. Yes. Yeah. I mean, yeah, it's like particle states. It's just that, yeah, the computation, yeah, it's a. I mean, it's like a sort of Feynman diagram of two particles going into two particles, but then you have this conformal transformation. This is a single worksheet, and you can write it like this, but and in the process, the number of strings can change, yes. Yeah, I can take, yeah, at the beginning, I said 3 strings going into 2, yeah, it can change, yeah. Yes. Yeah, yes. So you always get this delta of this. If you make all the momenta incoming, the total momenta should be 0. Then also the polarization should be such that they combine.
Do we also, like, if we can consider a particular type of scattering, for example, can I reproduce the scattering of two electrons, for example?
Well, I mean, so yes, I mean, yes and no. So the electrons, so still we have no fermion. So for that we have to have electrons, we have to go to the superstring. But yeah. But no, yeah, and the point is also that that as I was saying, so embedding the standard model in string theory, the way we do it is with the massless. So everything is from the massless sector because all the rest is too massive. And so how you put the mass, then it's more complicated. It was some Higgs mechanism or things like that. But yeah, but in principle, the computation of, yeah, so if here you put the vertex operator corresponding to some photon, this is just two, and this you can do then, this is two photons going into two photons, and yeah, and you get all the conservation laws that from the photons.
And do I get like the same amplitude that we get thinking of applying into something with normal field speed?
If you take, yeah, so if you take the alpha prime going to zero limit of that amplitude, yeah, you get the same amplitude that you will get doing, yeah.
Suppose a closed string is evolving into two open strings, or some interaction is there between a closed string and an open string. Can you give an example of an action which shows that interaction?
I mean, the action, so you can have, yeah, two photons becoming a graviton, but that's not what you want.
No, I mean, if there is an open string and a closed string, will there be two different world sheet metrics in the combined action?
Yeah, so you will have, if you write this, you will have the vertex operator of open string and the vertex operator of another open string. The problem is I didn't talk about vertex operator, so whoever, I mean, this becoming the x, the var x, so yeah, how so? But well, I'm being very schematic here, but yeah, so this interaction is possible. Yeah, I'm not sure what more to say about that, but yeah, that interaction exists, and I guess yeah, it's I mean, if you want to compute the loops, you have to do so one thing, something like this plus this with always two in the boundary and one in the middle, and you can do, and you can have you have conservation and everything. Okay, so the next thing so everybody asks me, okay, so we are doing strings in flat space. What about strings in curved space? So curved space is by background fields, I mean strings in the so strings in curved space, and also strings in some background B field or some background dilaton field. So these are all the massless, so these are the quanta of these are massless fields of the string, and then also, I mean, we have a mu, which is the massless state of the field corresponding to the massless state of the open string. And so I want to see, So I want to see what's the action. I want to see, I mean, many things that you've been asking about this. So let's first do the metric, which is what everybody asks about. So what about strings in a background metric? So first, I mean, we know the Polyakov action for that. We don't know how to quantize, but so the Polyakov action written in, so it's D2 sigma square root of minus h. So maybe I should do, well, my guy can do Euclidean or h alpha beta, the alpha x mu, the beta x nu, chi mu nu. Okay, so far so good. And now I'm going to do so I'm going to do two different things, expanding this metric, but in two different ways. So right now, let me think of an expansion around flat space. So let's take chi mu nu to be eta mu nu plus some gamma mu nu. So I'm doing an expansion around flat space. Now, if you compute, so or if I don't know, if you compute the, let's say, the partition function. Yeah, no, I don't want to talk about partition function. Let me not talk about partition function. Let me just do e to the minus s. Or, well, if I do e to the minus s, so this is e to the t over 2 integral of d2 sigma, or this is e to the minus s0, where s0 is this with eta mu nu. And then minus s1. So e to the minus s0 minus, or in this expansion, so I expand around e to the minus s0, so I have e to the minus x0, 1 plus this with gamma mu nu, right? 1 plus t over 2 integral d2 sigma square root of minus h alpha beta, the alpha x mu, the beta